So before we begin our study of calculus, let's review a few concepts first. So in this video we're going to review interval notation, equations of lines, slopes of lines, function notation, and some basic function operations like translations. So let's begin with interval notation first. So let's recall that if we're given two numbers a and b, with a less than b, then this notation, close bracket a comma b, close bracket, we call those brackets closed brackets, is a set of all numbers x that are between a and b, and x can equal a and it can equal b. So it's defined to be this set. Then we can have half open and half closed intervals like these two right here. So here we have an open bracket a comma b with a closed bracket on the right hand side. Now that's the set of all numbers x in which x is strictly larger than a and less than or equal to b. So the values x can take on the value of b but not the value of a. And then we have closed bracket a comma b with an open bracket on the right hand side. That's the set of all numbers x where x is bigger than or equal to a and strictly less than b. So x could take on the value of a but not b. And then we have an open interval. So we have the open parenthesis a comma b with another open parenthesis at the b. Now that's the set of all numbers x that are strictly between a and b but not equal to a and b. So this is the interval notation here that we will be using throughout the course. So for example, if we look at the closed interval -2 to 5, what that represents is it's all the numbers x between -2 and 5, and x can equal -2 and 5. So here we have that set graphed on the real number line down here. So notice it's all these numbers. We start at -2 on the left, and x can equal -2, so we fill that in with a circle, and then we just draw a line like this all the way over to 5. That's 5 right there, and we fill in with a circle right there. So this notation represents all the numbers from -2 to 5, including -2 and 5. So it would be numbers like -1.5, +1.7, 2.8, 4.9, and 5 as well. Now down here we have a half open interval. So here we have a half open interval, -2 to 5. Notice we have a closed bracket at the -2 and an open bracket at the 5. So that represents all the real numbers x greater than or equal to -2 but strictly less than 5. So we indicate that graphically like this. So we put a little closed circle at the -2, draw a straight line all the way up, and at the 5 we put an open circle to indicate that the x values cannot take on 5. So this set would represent numbers like -1.9, -0.5, 1, 2.8, 4.9, 4.99, 4.999, but not 5. Now here's our definition for intervals involving infinity. So this is the notation we use here to indicate the set of all numbers x that are bigger than or equal to a. So we put a little closed bracket at a, comma, and this is our positive infinity symbol right here. So this represents all the numbers from a all the way out to infinity. And graphically, we could represent that like this. If this is the number a on the real number line, we would put a little closed circle there, and it would be all of these numbers going from a all the way out to positive infinity. Notice when we write positive infinity, sometimes we'll put a plus in front of it, but oftentimes we will not. So if you don't see any type of sign in front of the infinity symbol, it represents positive infinity. We have the open set a to infinity. So that's just all the set of all real numbers x strictly bigger than a but not equal to a. So in that case we would just put a little open circle right here at the a, and it would be all the numbers strictly larger than a. Then we have the set notation like this: negative infinity to a with a closed bracket. This would be the set of all numbers that are less than or equal to a. So that would be like this if we were to graph it. That would just be all the numbers from a, put a little closed circle at the a, and just an arrow pointing down towards negative infinity in this direction. And then we have the open interval, negative infinity to a. So this is a set of all numbers x strictly less than a. So we would put an open circle right here, and then just an arrow pointing down towards negative infinity. So this is a notation we use when our intervals involve infinity. Notice one thing here: we never put a closed bracket at the infinity, so we never do this. That would be incorrect notation, because infinity really is not a number. It's not something that is included in your set like 1.5. It's more of a concept. It's not really a number. So we never put a closed bracket at the infinity. So for example, what would the set 3 to infinity with a closed bracket at the 3 represent? Well, that would be all the numbers greater than or equal to 3. So it would just be all of these numbers from 3 all the way out to positive infinity. So it would be numbers like 3, 3.5, 4.1, 5.8, and just continuing on to infinity. Now here's some notation for absolute values. We'll run into absolute values from time to time. Here's the strict definition for absolute value. You should be pretty comfortable with the absolute value of a number, but this is the strict definition of it that we will need from time to time. So the absolute value of a number x is defined to be the number x whenever x is positive, and negative x when x is a negative number. For example, if we want to evaluate the absolute value of negative 3, technically using this definition up here, this is our x value, negative 3, so it is less than 0, so we use this as our definition for the absolute value of x. So the absolute value of negative 3 is negative of negative 3, and of course two negatives being multiplied like that make a positive and just give us back positive 3. So this might seem like a strange definition because, for example, you may be used to just stating something like, well, the absolute value of negative 3 is just whatever the positive value of the number is. It's simply 3. And that's perfectly correct, but when we write it like this, as we'll see later on, it comes in handy to do this sometimes when we're dealing with functions in order to get rid of the absolute value symbol. So sometimes it's necessary to use this definition here. And of course, if you had something like the absolute value of 3, well, that's just 3. And if we follow the definition, that's exactly what we get back. The absolute value of 3, since 3 is positive, we use this piece of our definition, and so we just remove the absolute value symbols, and we get positive 3 back, of course. Now here's a theorem involving absolute values that we need from time to time. So the absolute value of x less than a, that's equivalent to all the numbers x that are between negative a and positive a. Or, using interval notation, it's equivalent to this set, negative a to a with open parentheses. The absolute value of x less than or equal to a, well, that's the same thing except we put closed brackets at the a and negative a, and we have less than or equal to here. Now these two definitions should make sense. For example, if we state what are all the numbers x whose absolute value is less than 3. Well, if we think of the number line here, if this is -3 and this is +3, well, if I pick a number like -2.5, is the absolute value of -2.5 less than 3? Well, yes it is, because the absolute value of -2.5, of course, that's equal to +2.5, and that is less than 3. That is true. So you see, this is going to be all the numbers from -3 all the way up to +3. Now it can't be anything greater than +3, because if we try to put 4 in here, well, the absolute value of 4 is not less than 3. And if we try to put a number like -4 in here, well, the absolute value of -4 is +4, and that is not less than 3 either. So you see, it would be all the numbers, the solution to this would be all the numbers from -3 up to +3. And if we put a less than or equal to here, all we have to do is that just fills in those circles there. Now we also have these two definitions down here, 3 and 4, or results I should say. If we want to find all the numbers x whose absolute value is bigger than a, well, that's going to be all the numbers x that are less than -a or greater than +a. Or written in interval notation, that would be like this. So it would be all the numbers from -a to -infinity, along with all the numbers from a to +infinity. This symbol right here is called a union symbol. That just means we combine both of these sets. So our answer is this set and along with this set. That's all that union means. If you're uncomfortable with that, you could just put a comma here. So now this definition, let's just look up here, see why that makes sense. Well, if I want to look at all the numbers x whose absolute value is bigger than 3, well, of course that would be numbers like 4, 5, 6, all the way to infinity, so it would be all these numbers. And also -4 would work here. If I put -4 in for x, the absolute value of -4 is +4, which is bigger than 3. So it's also going to be all of these numbers, from -3 to -infinity. So you see the solution to this, or rewriting this in interval notation, it would be all the numbers from -infinity to 3, along with all the numbers from 3 to +infinity. And the same thing if we put similarly, if we put a greater than or equal to symbol here, well then we would just fill in these little circles and we would have closed brackets then down here. Let's take a look at a few more examples working with these absolute values. So let's find all the numbers x that satisfy this inequality. So what we want to do, recalling that absolute value x less than a is equivalent to x being between a and -a, let's use this to rewrite this without the absolute value, so that would be the same as writing. Now what we want to do is isolate x in the middle. So we want to get rid of this number 1 right here. Well, to do that, we will subtract 1 from everything, from each term, and we get that. Now what we'd like to do is get rid of this number 2 right here. So what we'll do is we'll divide everything by 2, or multiply by 1/2. Now you have to remember your rules when you're dealing with inequalities. If we multiply by a positive number, the inequality does not change. Now as we'll see, if you multiply by a negative number, you do have to flip the inequality. So you have to remember that. So we'll divide everything by 2 here, divide this by 2, divide this by 2, divide by 2, or multiply everything by 1/2, and we end up with x being less than 4 and bigger than -5. So all the numbers x between -5 and 4 satisfy this inequality up here. For example, if I say x is 3, well, notice that if we put 3 in here for x, we get 6 plus 1, that's 7. Absolute value of 7 is less than 9. On the other hand, if I pick a number x that is not in here, like say 6, well, if I put 6 in here for x, I get 12 plus 1, that's 13. Well, the absolute value of 13 is not less than 9. So the solution to this would be, we could either write it like this, or using interval notation, we could write it as -5 to 4 with open brackets. So that would be our solution to this problem. All the x values between -5 and 4 satisfy this inequality. Now let's take a look at this one. So we do the same thing. We set up, now we want to isolate the x, so we're going to get rid of this 3 first by subtracting 3 from each term. And when we do that, we're going to get, now we have to get rid of this -2. So what we're going to do is divide everything by -2, which is the same as multiplying by -1/2. Now if you multiply by a negative number, multiply or divide, remember by rules of inequalities you must flip your inequality when you do that. So when we divide by -2 everything, we must flip these inequalities. These inequalities must be flipped like this when we divide by -2. And what we end up with then is -18 over -2 is 9, is bigger than or equal to x, is bigger than or equal to, and this is -6. And let's just reorder this so we have the smaller number on the left, the larger number on the right. So this is equivalent to saying x is less than or equal to 9 and bigger than or equal to -6. And so all the numbers x in this interval satisfy this inequality. And we could write our solution set as -6 to 9 with closed brackets like that. Notice if we pick a number in here like 8 and put it in here for x, if we put 8 in for x, we would get 3 minus 16. Absolute value of that is -13. So, I'm sorry, we get the absolute value of -13, which is +13, and that is less than 15. On the other hand, if we pick a number that's not in here, like 10, if I put 10 in here for x, we would get the absolute value of 3 minus 20. Well, that is absolute value of -17. That is +17, but that is not less than or equal to 15. That's actually bigger than 15. So 10 does not work up here for x. Well, that's what our answer told us. All right, now let's take a look at this. So here we're going to review equations of lines and slopes of lines interpreted as a rate of change. So first of all, let's recall what the slope of a line is. So if we're given a line in the plane between 2 points, x0, y0, and x1, y1, then the slope of the line is defined to be rise over run. You should have seen that before, which in this case, using these points, we can also write that as y1 minus y0 divided by x1 minus x0. Now you may also see this written as a change in y divided by a change in x. So y1 minus y0 represents a change in y as you go from y0 to y1, and the change in x is the distance from x0 to x1. Notice this notation we use this little, that's called a delta symbol, to represent a change in some variable like y or x. That's very common notation that we'll see used later on when we discuss the derivative. Now it's important to note this. It's important to note how to properly interpret the slope. If you're given the slope of a line, the best way to think of that is as follows. if we think of increasing an x value by 1 unit, so if we're sitting on the line and we increase x by 1 unit, so we move to the right 1 unit, then the y coordinate will increase by the value of the slope, whatever that number happens to be. And if the slope is negative, then the y value will decrease. It'll actually drop down. Let's take a look at a little graphic here to understand this a little better. So here we have a line, and it's passing through these 2 points. And move that down a little bit for you. There we go. So here we have a line that's passing through 2 points here, x0, y0, and x1, y1. So notice that the change in y is going to be this distance. That's our rise. So that is y1 minus y0. If we take the difference of these 2 numbers, that's what we get. We get the rise. And if we take the difference of these 2 numbers, we get the run. So if we evaluate rise over run, well, that's what our slope represents. Now, it's also important to note that if you look at this definition up here, when we go y1 minus y0, we have to go x1 minus x0 in the denominator. So it doesn't matter if we went y0 minus y1, but if we did that, then we would have to keep the same ordering in the denominator. We would have to go x0 minus x1 then. So it doesn't matter how you order the difference in the numerator and denominator as long as you're consistent. So in other words, you could write that as y0 minus y1, but then you have to go in the denominator x0 minus x1. Now this number, the rise over run, also note that if we are sitting at this point right here, and if x only increases by 1 unit, say that distance is 1, then the y value will increase by the slope value. So this would be the slope, whatever the rise over run would happen to be. And if this number is negative, well then the y value would actually decrease if this were negative. Now let's take a look at an example. So here we want to find the slope of the line between these 2 points. So our slope is going to be the difference in the y coordinates divided by the difference in the x coordinates. So let's pick this point right here as being x1, y1, and this one as being x0, y0. So then if we take the difference in the y coordinates, let's write this as 3 minus 2. So that's the difference in the y coordinates. Then since we did the 3 first, that means when we take the difference in the x coordinates, we have to do this 2 right here first. So then the difference in the x coordinates will be 2 minus negative 1, and we get 1/3. So that is the slope of the line between those 2 points. And if we interpret this graphically over here, I inserted a Cartesian plane right here. If we graph these 2 points, negative 1, 2 would be right about here, and 2, 3 would be right about there. So our line would look like this. So that's roughly what the equation of our line would look like. And so this line would have slope 1/3. So it's important to note that what that 1/3 means is if we're sitting right here on the line, if we go over 1 unit to the right, to get back on the line again, we will have to go up. That distance would be 1/3 right there. It's a little tough to see because it's sort of small, but that distance upward would be 1/3. So if we go 1 unit to the right to get back on the line, we would have to go up 1/3 of a unit. And so that's how we interpret this slope. If this were a negative number, then what that would mean is we would go down 1/3 to get back on the line, and our line would have looked like this. It would have been leaning in this direction. All lines with negative slopes, remember, lean in a direction like this. Positive slopes, they lean in a direction like this. Or lines with positive slopes are increasing. Lines with negative slopes are decreasing. Let's look at this example. So let's find the equation of the line passing through the point 1, 3, having a slope of 2. So here what we're going to do is this. To solve this problem, let's look at it graphically down here. So here we have the point 1, 3 sitting right here. And here we have any other point on the line, just call it xy. So if we create a right triangle like this, notice that this distance would be y minus 3. This distance would be x minus 1, so our rise is y minus 3, our run is x minus 1. Now our line is supposed to have a slope of 2. So if we set our rise over run equal to our slope, then we end up with this equation, and there's the equation of our line. That's all we have to do. Now this is a particular form for the equation of a line. This is called our point-slope form for the equation of a line. So this is point-slope form. Notice here we call it point-slope form because we have the slope 2 right here, and we have the point 1, 3 sitting with the x value and the y value. So this is our slope, oftentimes denoted as the letter m, and the 1, 3 that forms our point right there. So this is called the point-slope form for the equation of a line. Now, we can take that and write it, put it into what we call slope-intercept form if we just do this. So simplifying this, let's write this as y equals, now if I distribute this 2, that's going to be 2x minus 2, and I add the 3 over to the other side, and we end up with, and that's a very common form also, this is called our slope-intercept form. Now it's called slope-intercept form because this 2, once again, represents the slope of the line, and this 1 right here is actually our y-intercept. That's where the line crosses the y-axis. Notice if we put 0 in for x, we get back 1 for y. So this is our y-intercept, and this is our slope. Notice over here on the graph that 1 is right there on our y-axis, so that's our y-intercept. And the slope of this line is 2. Once again, notice that if we go over 1 unit in the x direction, we will have to go up 2 units to get back on the line again. Now it doesn't look like we went up 2, that's because the scaling is off. Notice that this the x-axis goes from 0 to 5, whereas the y-axis goes from 0 up to about 12. So the scaling is off a little bit. Notice that we went from 3 up to about, that's 5 right there. So as x, if we increase x by 1 unit, when we go from 1 to 2, the y value has to increase by 2 units to get back on the line again. And that's the way we should think of the slope. If x increases by 1 unit, the y will increase or decrease by whatever the slope is. Now let's take a look at this example. Let's sketch the graph of y equals 3x plus 4. Well, as we have it sitting here, this is in slope-intercept form. So the 4 is our y-intercept. So this point right here will be on the graph of our line. That's the point 4 on the y-axis right there. And our slope is 3. So if we go over 1 unit, now this is 1 right here on the x-axis. If we go over 1 unit, that means we will go up 3 units. So 5, 6, 7 roughly. Right there would be another point on the line. So this is the point right here. That's the point 0, 4. And this point right here, if we go over 1 unit, we have to go up 3. That will be the point 1, 7. So there are 2 points on our line, and then we just have to connect with a straight line going through those 2 points. And that would be the equation of our line right there. It would look something like that. Now if the 3 right here were negative, let's just do this. Let's say this 3 were negative, so let's say we want to sketch the graph of, well, in that case then, if we were sitting here and we went 1 unit to the right, then we would have to go down 3 units. So we would have to go down to here and then just connect those 2 dots with a straight line. And so that would be a rough sketch of the equation of our line. So notice if we go over 1, we would have to go down 3 because our slope here is negative in this case. Now here let's do a review of horizontal and vertical lines. So for a horizontal line through any given point x0, y0, the equation of that line is simply going to be given by y equals y0. Also notice the slope of any horizontal line is always going to be 0. So for example, let's sketch the graph of y equals 5. Well, right here we have 5 on the y-axis right there, and so we just have to draw a horizontal line through that point on the y-axis. So right there is what our equation would look like. Notice that for every point on that line, notice that the y-coordinate is always 5. So that's why we say the equation of this line is given by y equals 5. Because every point in the Cartesian plane where y equals 5 is on that line. Also notice that the slope is 0, because if I pick any point here, say I pick a point right there, if we go over so many units, well, we don't go up or down at all. So our rise is always 0. So the slope of this line is always going to be of the form 0 divided by our change in x, and that is always going to be 0. 0 divided by any number is 0, unless delta x is 0, but we're assuming delta x is positive, some positive or negative change in this case. Now let's recall that a vertical line through any given point x0, y0 is given by the equation x equals x0. And also notice the slope of a vertical line is undefined, as we'll talk about in a second. So for example, let's sketch the graph of the line x equals 5. Well, right here we have 5 on the x-axis, and so we just have to draw a vertical line going up and down through 5 on the x-axis. Once again, notice that if I pick any point on this line, it's going to be of the form 5, y. So the x-coordinate is always equal to 5 for every point on this line. So that's why we say x is always equal to 5. So all the points in the Cartesian plane where x is equal to 5 is going to be on this vertical line. Now notice the slope is undefined for this line, because if I pick any point on the line, say right there, well, and then I move up to this point, well, notice as we go from here to here, if we try to look at a change in y divided by some change in x as we move from this point to this point, notice that the change in y is going to be some positive number. Oh, in this case, say it's 2 or whatever. But our change in x, it doesn't move. The change x is always 5, so our change in x is 0. Well, any number divided by 0 is an undefined quantity. So the slope of any vertical line is always undefined, because if you try to evaluate the slope, you end up dividing by 0 because the x-coordinate never changes. So here's a summary of equations of lines that you'll see. The general form for an equation of a line is a times x plus b times y equals c. So perhaps something like 3x plus 5y equals 7. That would be a general form for the equation of a line. And then we have a point-slope form for the equation of a line, written like this. So notice in this form our slope is m, and the point that the line happens to pass through is x0, y0. That point would be given to you, and m would also be given to you, and that represents the slope. The slope-intercept form is right here. So the b is actually the y-intercept, and the m is the slope again. Notice if we set x equal to 0, we get y equals b, so that's where the graph crosses the y-axis. And then horizontal and vertical lines. Horizontal line is given by an equation y equals y0, where y0 is some constant that would be given to you. Also notice that the slope of a horizontal line is always 0. And then we have a vertical line, x equals x0, for some number x0 that would be given to you. And the slope of any vertical line is undefined, or we say d, n, e, does not exist. Now let's take a look at parallel and perpendicular lines. So if we're given two lines, say y equals m1 x plus b1, where m1 and b1 are just some numbers, and we consider another line y equals m2 times x plus b2, then the two lines are parallel if and only if their slopes are equal. That makes sense. Parallel lines have the same slope, so the slopes would have to be equal. Now this one's not immediately obvious, but it also happens that the lines will be perpendicular, cross at 90-degree angles to each other, if and only if m1 is the negative reciprocal of m2. So m1 equals negative 1 divided by m2. Or that's the same as saying m2 is the negative reciprocal of m1, so m2 equals negative 1 over m1. These two equations are the same. If you were to take one equation like the first one, multiply the m2 over to the left, divide the m1 to the right, you would end up with this equation. So these are equivalent equations. So let's take a look at this example. So first of all, let's find the equation of the line passing through the point 1, 3 that is parallel to this line. Alright, so we have to find the equation of a line. Well, we're given a point that the line passes through. So our point is 1, 3. Now to find the equation of any line, we need a point and we need a slope. So we don't know what the slope is. Well, our line is supposed to be parallel to this line, so that means they have to have the same slope. So we need to find the slope of this line right here. So to find the slope, we need to put it in slope-intercept form, and then just read off the slope. So if we take this equation, and we put it into slope-intercept form, so there we have it in slope-intercept form now. Notice that when we have negative 2x plus 5 over negative 3, we merely split this fraction up. So we use the rule that a plus b divided by c equals a over c plus b over c. We split it apart like that. Now you can only do that if the a plus b is in the numerator. Keep that in mind, remember that. If you had something like a over b plus c, you could not split this up as a over b plus a over c. That doesn't work. Only works when the addition is in the numerator. So now going back to our problem here, now we can read off our slope. Our slope here is 2/3. And negative 5/3 happens to be our y-intercept, but we're not really going to need that right now. So therefore, our slope up here we've now found out is 2/3. And so therefore the equation of our parallel line is going to be y minus 3. And there we go. Notice we have it in point slope form now. And if we want to put this into slope intercept form, we would just have to distribute the 2/3 and take the 3 over to the other side. And what we would get is keep in mind 3 here, finding a common denominator. That's 9/3 minus 2/3, so that's going to be plus 7/3. And there's the equation of our parallel line. And graphically, we have that over here. So right here, the blue line here, this line right here, labeled by 2x minus 3y equals 5, that's our original line. And the line that we found is this one right here. So that's our line parallel to this one and passing through that point right there, which is 1/3. And our y-intercept right there is 7/3. Now let's find the equation of the line that's perpendicular to this line and passing through the point 1/3. Now to find the equation of the perpendicular line, well, let's notice that the slope of the line that we're given, we already found that to be 2/3. So therefore the slope of the line that we want is going to be the negative reciprocal of this. So the slope of our line that we want is going to be, slope of the perpendicular line is going to be negative the reciprocal of this, so negative 1/2/3. And that you can simplify. Remember, you just have to flip this fraction up to the top, and it's going to be negative 1 times 3/2, or negative 3/2. So there is the slope of the perpendicular line. So therefore the equation of our perpendicular line is going to be y minus 3. So there we go. So that's the equation of our perpendicular line, and then just simplifying that to put it in slope-intercept form, we get, and then just simplifying this, keep in mind 3 is 6/2, so 3/2 plus 6/2 is going to be 9/2. And there's the equation of our perpendicular line. And that's what we have graphed right here. Notice that we have a 90-degree angle right there. This was the line that we were given right here. This line right here is the one we were given. And this line right here is the perpendicular line to it. So notice that this line has a slope of negative 3/2, and well, it looks like it should have a negative slope. It's leaning in this direction. Its y-intercept is 9/2, so that point right there would be 9/2 on the y-axis. And it does look like it is perpendicular to the line that we were given. Now let's review the slope as being a rate of change. Now we mentioned this earlier, so we're just going to look at one example here. If we're given a line with a slope m, and we are currently, suppose we're sitting at a point xy on that line, then if we increase x by 1 unit, then the y value will change by m units, whatever the slope is equal to. So we interpret the slope as telling us how much y will change for each 1 unit change in x, and we call this a rate of change. For example, in the graphic we have right here, so here we have the line y equals 2x plus 1. So it's graphed right here. Now suppose we are currently at the point 1,3 on this line. Notice if we put 1 in for x, we get 3 back for y. Then if we move to the right 1 unit, to get back on the line, we will have to move up 2 units. And then we are sitting at the point 2, 5. Notice if we put 2 in for x, we get back 5 for y. And so our slope here is, of course, 2 divided by 1. And so we see that we interpret that number as representing a rate of change. If x increases by 1 unit, y must increase by 2 units. And keep in mind, if this 2 were negative 2, say we were considering y equals negative 2x plus 1, then if we move 1 unit to the right in the x direction, we would have to move down 2 units in the y direction. So we would have something like this in that case. So here we have the graph of y equals negative 2x plus 1. You notice we have 2 points on the graph, negative 1, 3, and 0, 1. Notice if we put negative 1 in for x, we get back 3 for y. And if we put 0 in for x, we get back 1 for y. And notice if we're sitting at the point negative 1, 3, if we move over 1 unit in the x direction, then we have to move down 2 units in the y direction to get back on the line again. So this would be negative 2 here. And so our slope is rise over run, negative 2 divided by 1, or negative 2. And so that's how we interpret a negative slope. So let's take a look at this example. So suppose we're traveling in a car along a highway, and you notice that since the start of your trip 2 hours ago, you have traveled 90 miles. Now let's assume that you traveled at a constant velocity during your drive. So you perhaps were on a highway, traveling at a constant speed down that highway. You didn't run into any lights or any traffic. Let's find the position function of your car and interpret the slope of the position function. Alright, so we want to find a graph of our position function. Well, let's notice that when you started your trip, let's say that was at time 0, your position was 0. You were 0 miles from your starting point. Say you started at home. So you were 0 miles from home. Then after 2 hours, when t equals 2, you are now 90 miles from your starting point. So therefore the graph of your position function will pass through these 2 points. So here are the 2 points on the graph of your position function, 0, 0, and 290. So now we can find the equation of our position function as follows. We just have to find the slope of the line between these 2 points. Well, the slope is going to be 90 minus 0 divided by 2 minus 0, and that is 45. And then the equation of the line is just going to be y minus, we'll pick one of these points like 0, 0, y minus 0 equals 45 times x minus 0. So in other words, or we'll put t in place instead of an x, we'll use the letter t for time. And we get the equation of our line, our position function, y equals 45 t, which we have right here. All right, now let's interpret this 45. Now that's the slope of our line, so let's see what it represents. Well, let's recall that the velocity is distance divided by time. How far you travel divided by how long it took you to travel. So it took you 2 hours to travel 90 miles. So if we look at 90 over 2, notice you get 45 miles per hour, which is the slope of your line. So in other words, the slope of your position function represents the average velocity of your car from time 0 to time 2 hours later. So down here we have the graph of our position function. This line right here is the graph of y equals 45 t. And notice that the slope of this line is 45. So if we go over 1 hour in time, we will move 45 miles. So if our time changes by 1 hour, our position changes by 45 miles. And so our slope m is 45 miles divided by 1 hour, or 45 miles per hour. Notice how the units work out here. The units for the y are miles, the units for our t-axis are hours, and so our units for the slope are miles over hours, or miles per hour. And you see the slope actually gives us our average velocity during that trip. And so that's how we can interpret the slope as being a rate of change.